Ranj, can you hear me? Can you hear me? Can you guys hear me? Can you guys hear me? Can you hear me? Jason, can you
Huh?
can you hear me?
Yes, I can.
Can you hear me?
Yes, I can, sir.
And can you see the screen?
Yes.
Okay. when I move the arrow on the screen, can you see the arrow?
Yes, I can.
Okay. Yeah, I forgot to bring my iPad today, so I'm using my desktop computer, so I can write on it. I don't know if you guys try to listen to the cloud recordings. Anybody try?
No, I haven't tried.
Okay, I think we'll get started. Can you guys hear me and see the screen? If one of you could unmute yourself momentarily. Can you hear me?
I can hear you.
Okay, and see the screen, right?
Yeah.
Okay. All right, let's get started. Hope you guys are doing okay with all this social distancing and staying at home. It's kind of tough, I know. All right, so today we're going to start off on a new topic of capacitance. So far we've been looking at current voltage characteristics, but now we'll look at charge voltage characteristics. Now in freshman physics, we all learn about fixed parallel plate capacitors, and we know that if you have two metal electrodes separated by a distance W with an area of the electrode A, then we know that if the dielectric constant of the dielectric is epsilon, the capacitance of a fixed parallel plate capacitor is given by epsilon times the area of the electrodes divided by the thickness of the dielectric. Okay. Now, such capacitors are fixed voltage independent capacitors. And in that case, you can define the capacitance as charge stored on either electrode, plus Q or minus Q on the other electrode, divided by the voltage that you apply across them. Now, clearly, if you have a linear relationship like this, if you plot charge on the y-axis as a function of applied voltage on the x-axis, you should get a straight line whose slope is your capacitance. Now, the important thing to note over here is that anytime I talk about capacitance, it is the ability of a circuit element to store charge. So anything that can store charge will have a capacitance. Similarly, and that stores electrostatic energy, half epsilon electric field square that you hopefully remember from your 325. Similarly, an inductor is any element which can store magnetic charge, half h squared divided by mu, right? And in the case of that, of an inductor, that's given by half Li squared, while in the case of a capacitance, that stored energy is half Q squared over C. So these are things that you learn in freshman physics or in 325, okay? Now, what you have to do when you talk about capacitance in the context of semiconductors is generalize this description, because one finds that the stored charge in a semiconductor device Q in general will not be a linear function of the applied voltage, but rather will be a non-linear function. And in that case, all that I have to do is generalize this definition of C, and instead of calling it Q divided by V, if it's a non-linear function, you define the capacitance in a differential form, dq, the change of charge, divided by dV, the change of applied voltage across the semiconductor device. And since the Q over V is a non-linear curve, the slope will be different at different points. So that gives you a voltage dependent capacitance. Okay. So it's a simple generalization of the concept of a capacitance. You could do the same thing for resistors also. You will see that in a diode, for example, you've already seen that if you look at the IV characteristics, it's not a linear curve. It's an exponential function of current as a function of voltage. So there also you have to define the resistance or conductance of a diode as, the conductance will be defined as di dt, or the resistance as dv di. Okay, so these are obvious generalizations. So let's apply this concept of generalized capacitance to the PN junction. Okay, so once again, a capacitance is the ability of a device to store charge. There's two flavors of charge that we'll talk about in the context of a PN junction. The first is the exposed dopant charges in the depletion region, okay? And that's going to give rise to what's called depletion capacitance. And in a second, we'll also talk about stored minority carrier mobile charges, and that gives rise to another type of capacitance known as diffusion capacitance, okay? So here, what I'm looking at is one-sided abrupt PN junction. One-sided means the doping on one side in this case, the P side is assumed to be very, very large. So I'm showing that as P plus. So as a result, when I apply a reverse bias VR, the depletion region extends mostly on the N side. Okay. Of course, it'll have to extend on the P side also, but if the P doping is very large, we know the depletion width over here is going to be negligible. So I'm not showing that on this figure. Now remember, we said that the total number of dopant charges on either side have to be exactly the same. So W times ND must be equal to the depletion width on the P side, that's not shown, times Na. Okay, because the reason you form these exposed dopant charges is when I join the N and the P region together, the mobile electrons spill over, recombine with the holes, and in the process, every time I expose a donor ion, I have to expose an acceptor ion on the other side, right? So the total donor charges that are exposed must match the total acceptor ion charges, all right? Now, you might ask, am I not violating space charge neutrality in this region? And the answer is yes, because remember I told you that space charge neutrality is not a universal concept. It's only true if the doping concentration profile is more or less constant, as in this region. Now, at the junction itself, we know that the doping changes abruptly, in this case, from a high P-type doping abruptly to a lower N-type doping. So in the vicinity of the region where the doping charges are varying abruptly, space charge neutrality breaks down, and you do have exposed dopant charges, okay? And those exposed charges or stored charges give rise to what's called the depletion capacitance. Now, as I said, you can't define this capacitance as simply the stored charge Q, which in this case is the electron charge small q times the doping density Nd per unit volume. So that gives you the dopant charges per unit volume. And then to get the total charge, you have to multiply that by the cross-sectional area A times the depletion width W, right? So A times W is the depletion volume. QND is your exposed dopant charges per unit volume. So QND times the depletion volume, A times W, will give you the total number of exposed charges Q, all right? For a certain reverse bias VR in this case, okay? But in this case, you can't define the capacitance as this Q divided by the VR because it's a nonlinear dependency of Q on VR. Now, why is it nonlinear? Well, that can be seen by looking at the denominators over here. If you recall the electrostatic behavior of a PN junction, one of the expressions that we derived, and I've told you is very, very important that we'll be using again and again, is if you square both sides of the denominator, what do I get? I get Q squared equal to 2 epsilon total voltage, which is the built-in junction potential, minus the applied reverse bias, minus the applied bias, either forward or reverse. So in this case, I'm applying a reverse bias, so that would be V naught plus VR divided by Q times the doping charge on the N side, okay? And if I flip that, I'll get the total voltage across the junction, which is V naught plus VR in this case, equals half, because I'm flipping this over to the left-hand side. So V naught plus VR would work out to be half QND W squared over 2 epsilon. Remember, that's an expression that we derived for the electrostatic behavior of a PN junction. And I told you it's a very important relationship that we'll be using again and again in different contexts. So this is one of those contexts, okay? So that expression, if I take the square root of both sides and I flip terms over, I end up getting W, the depletion width, equal to this thing in the denominator, square root of 2 times the dielectric constant of the semiconductor times the total voltage across the depletion region, which would be V naught plus V reverse in the case of reverse bias, or V naught minus forward bias if it's forward biased. So as a result, you see that with reverse bias, the depletion region is going to expand and the total voltage across the junction is higher, while in forward bias, the total voltage across the junction is reduced by whatever the forward bias is, and the corresponding depletion width collapses, okay? Now, this is true only if I have assumed a one-sided abrupt PN junction. So in this case, I can ignore the depletion width extending on the P side. Therefore, I can ignore the voltage drop on this side, right? Because the voltage equals electric field times distance. So if the depletion width is negligible, the voltage drop on the depletion region on the P side is going to be negligible. If that wasn't true, then the expression becomes a little bit more complicated, but the functional form stays the same. Okay. All right. So I have W given by this. What I now need to do is, if I change the voltage across the junction from VR to VR plus delta V, I have to figure out how much the depletion region extends from W to W plus dW, and therefore there's a corresponding change of charge QA doping concentration times dW, and that's the shaded region over here. Okay, so what I need to do is to use this differential form for the capacitance. I have to relate this dq QAND dW by dV. But notice over here I have dW, right? So I have to change variables from dW to dV. How can I do that? Well, I already have a relationship between W and V. So if I take dW, I take the derivative of this, and I get that times dV, okay? And that will then enable me to come up with an expression for dq over dV. All right, you guys with me? So I have charge given by this. What I want to do is to get the differential relationship. So I increase the reverse bias from VR by a delta amount, delta V, and I see what the corresponding change of the depletion width and therefore the depletion charge is, and I have to figure out the dq divided by delta V. Okay, to do that, I need a relationship between W and voltage, but I already have that over here, right? So I can simply take the derivative of that and change variables from dW to something in terms of dV, and then I can take the ratio of dq over dV. Okay, I'd urge you to do that math, on your own, and what you'd find is something very, very interesting. So if you did that math, you'd end up getting an expression for the depletion capacitance equal to this divided by this quantity, which is nothing but the depletion width. In other words, the expression for the depletion capacitance is the dielectric constant of the semiconductor times the area of the diode divided by the depletion width. What does that look like? Very interestingly, that's exactly the same functional form that we have for a fixed parallel plate capacitor, where this undepleted region is one electrode. This undepleted region can be thought of as the other electrode, and this depletion region can be thought of as a dielectric between the two electrodes, very much like that of a metal plate capacitor, except that now the dielectric that you have between the two electrodes is not a fixed dielectric. It's a dielectric thickness which depends on the applied voltage. So as you increase the reverse bias, the depletion region expands. In other words, the dielectric thickness increases. And as a result, if I now replace this depletion rate by the dependency on voltage, you end up getting a voltage dependent capacitance. Okay. So in terms of the physical picture, it's as if that if I change the reverse bias by a small amount, I wiggle the edge of the depletion region over here as shown by this dashed region. And therefore I have this as one plate, this as one plate, and the depletion region in between is kind of like your dielectric, except that it's not a fixed dielectric, it's a voltage dependent dielectric thickness. And that's why you end up getting a voltage dependent capacitance dq over dV. You guys with me? All right. So now if I plot this capacitance as a function of the applied bias, now remember in the case of reverse bias that V would be minus VR. So this ends up become V naught plus VR. While in the case of forward biases are considered to be positive. For forward bias, that will be V naught minus V forward. While for reverse bias, it will be V naught plus magnitude of VR. Okay. So if I increase the reverse bias, the depletion region is going to keep increasing, and the capacitance drops as 1 over square root of the voltage. Okay. For high reverse biases, you can kind of ignore the V naught with respect to the VR, because V naught we have seen is of the order of 0.6, 0.7 volts. So if you apply high reverse biases of the order of, say, 10 volts, 20 volts, this is approximately equal to the magnitude of the reverse bias. Okay, so you end up getting a 1 over square root of applied voltage dependency. On the other hand, if you applied a forward bias, now forward biases are considered to be positive, the depletion region collapses, and therefore the capacitance increases. And in principle, if the forward bias was equal to V naught, this would go to 0 and the capacitance blows up to infinity. But of course, that never happens, because what ends up happening is as you increase the forward bias, the forward current keeps going up exponentially, and most of the voltage then would drop across this series resistance and this series resistance, and you could never reduce the total voltage across the junction itself to 0. Okay. All right. Now, once you get the idea about depletion capacitance, I derived that for one-sided abrupt PN junction. If you did the same math for doping concentrations which are comparable on the two sides, now you'd have the depletion region extending not only on the N side, but also on the P side. That becomes a general form of the expression. Phi I is the same as a V naught in the previous expression, and VA is the applied voltage. So this is just a simple generalization of the previous expression to two-sided junctions. All right. Now, one interesting thing that you see is if I take the square of both sides and you take the reciprocal, I obviously get 1 over C squared. I get rid of the square root and I flip it, and I end up getting this. So a plot of 1 over C squared as a function of applied voltage should give you a straight line whose slope would depend on this parameter, right? Now, this is all constants. That's electron charge. That's a dielectric constant of the semiconductor, which is the material constant. And this depends on the doping on the two sides, all right? So what this expression tells us is if I replotted the CV data as 1 over C squared as a function of voltage, from the slope, I should be able to get an idea of the doping concentration, all right? Now, in this case, I have doping concentration on both sides, but if it was a one-sided abrupt junction, as in the previous example, I'd simply have the ND term over here, and I could extract the value of the ND. Okay, so it turns out this is, so that's what's shown over here. So if I have a one-sided abrupt PN junction, as on the previous slide, you only get the ND term over here. So this would be a way of extracting the value of the doping concentration on the lightly doped side from the plot of 1 over C squared as a function of voltage and taking the slope of that. Okay. So this particular technique for measuring doping concentration is known as CV profiling. So I plot the capacitance as a function of voltage in a funny way. I plot it as 1 over C squared as a function of voltage, and from the slope I can get a measurement of what the capacity of what the doping concentration is. Okay, it's a very powerful way of measuring doping concentrations in a semiconductor device. The next few slides, you're not going to be responsible for in the exams because we lost some time, but I'll quickly go over it just for the sake of completeness. And this is something that I'd actually mentioned in passing before spring break. So what we had said was, if you look at the variation of the doping concentration as a function of distance in the depletion region, so far the math that you've been doing is in terms of what I call abrupt junctions. And what that means is, I assume that the doping concentration is constant on the P side at some constant value of Na, and it changes abruptly to another doping concentration Nd on the other side. Okay, those are called abrupt junctions. So constant doping changing abruptly at the junction to another constant doping. One-sided abrupt junctions would be if the doping on one side is much, much higher than the doping on the other side, in which case it can ignore the depletion region extending on the heavily doped side of the junction. So one-sided abrupt junctions are a special form of abrupt junctions, all right? But as I've told you, not all practical PN junctions need have a doping concentration which is constant and change abruptly to another constant doping. In fact, in practice, when you make a PN junction, you may start with a semiconductor wafer with a constant doping shown by this dashed line. So in this case, I'm assuming I have an N-type doping, which is uniform throughout the wafer. And then I form a mask and I implant or diffuse dopants in, as I mentioned in section 5.1. And if you do that, I'm liable to get a more or less linearly varying doping profile of the P-type dopant shown in blue over here. Okay. Now, where is my junction? My junction is in the form wherever the P-type doping matches the N-type doping, which is at this point. All right. Now you'll notice that if you look in the vicinity of this junction, the doping concentration doesn't really change abruptly, right? It's not a constant doping changing abruptly to another constant doping. In fact, in this particular example, it's more like a linearly varying doping, and that's what's shown in this figure down below, right? So if I plot the difference of the doping on the two sides, it's varying linearly from a P-type doping to a N-type doping as shown over here. Now, what is the impact of that? Well, if my depletion doping concentration is varying linearly, the charge is varying linearly. To get the electric field from that, we saw in the analysis of the electrostatics of a PN junction, I have to solve the Poisson equation, which is dE dx, E being the electric field, equal to charge distribution, shown over here, divided by epsilon, right? Now, in the case of an abrupt junction, the charge distribution was assumed to be constant, changing abruptly to another constant. If I integrate a constant, that's why I had initially got electric field, which varied linearly, changing linearly like so. And then when I get the electrostatic potential, I have to use minus dV dx equal to the electric field. If the electric field varied linearly, if I integrate that, I got a variation of the electrostatic potential, which is parabolic, changing to another parabolic shape. And therefore, the band diagrams also match that shape, right? Except that it was a mirror image, meaning that where the electrostatic potential went up, the band diagram went down, and vice versa, right? Now, all that's going to happen in this case is I pick up another power of x, x being the position, right? So now the charge distribution isn't constant. The charge distribution itself varies as x. Therefore, the electric field, which is dE dx equal to the charge distribution, if I integrate that, the electric field now varies as x squared. So the electric field curve is a parabola. And then the electrostatic potential, which is minus dV dx equals electric field. To get the electrostatic potential, I have to integrate the electric field. So now if the electric field varies as x squared, how would the voltage vary? It varies x cubed, right? So you pick up an extra power of x. That's all there is to it, okay? In fact, you can generalize this to, if I had a doping concentration, say an abrupt doping, so I have a very high P-type doping, I don't need to worry about the depletion region on the other side. But on the N-type side, I have a doping variation with position as some constant x to the power m, okay? So then, in the Poisson equation, I'd get dE dx equal to charge, which is given by this, divided by epsilon. So if I get the electric field, I have to integrate the charge. So the electric field would vary as x to the power m plus 1. And then the potential would vary as x to the power m plus 2, right?
Professor,
Yes.
could you go back to the last slide real quick?
Sure. Yes.
So in our previous studies of these junctions, the electric field has been at a maximum at the junction point, but in this case, it's a minimum. What's the...
No, this is also, the magnitude is a maximum. So this is a sign of the electric field, okay? So in the previous case also, remember we had a triangle which pointed downwards, right? So just think of the electric field magnitude, okay?
Okay.
Yeah, so the electric field lines will extend from the positive charges to the negative charges, okay? So on this side, I don't have any depletion region, so the electric field would be 0. And then you imagine electric field lines from the positive dopants to the negative acceptor ions, okay? And then if you take cross sections, you'd find that right at the middle, all these field lines would cross the plane at x equal to 0 over here, right? So that's all that I'm showing. So the reason this is shown as negative is the field lines are pointing in the negative x direction. Okay.
Okay, thank you.
So electric field is a vector, of course, right? So you really have to think of the magnitude of the electric field. All right, so that was a good question. So all that I was trying to say was, if I have a power law dependency of charge as x to the power m, if you integrate that, the electric field would vary as x to the power m plus 1 once I integrate the charge according to the Poisson equation. And since voltage is related to electric field as minus dV dx equal to electric field, voltage equals integral of the electric field. So voltage would vary as x to the power m plus 2. Okay. You could do the same kind of analysis that you did for the depletion capacitance for abrupt doping, and you'd find you get a complicated dependency of capacitance in terms of the power law dependency of the doping, as shown over here. Okay, but I'm not going to make you responsible for this part in the exam, but you should read through it on your own. Okay. So that's all that I have about depletion capacitance. So once again, capacitance is the ability of a device to store charge. Now, in a fixed metal plate electrode capacitor with a fixed dielectric, capacitance equals charge Q plus Q on one electrode or minus Q on the other electrode divided by the voltage across electrodes, and that works out to epsilon A being the area of the electrodes, divided by W, if W is the dielectric thickness. In the case of the semiconductor depletion capacitance, interestingly enough, if you do the capacitance analysis, although the capacitance should be defined as a voltage-dependent capacitance dq dV, if you do also the math, interestingly enough, the expression looks very similar to that of a parallel plate capacitance. Epsilon, area of the electrodes, which is the area of the diode, divided by the thickness of the dielectric, in this case, the dielectric being the depletion region, okay? But of course, the dielectric is now not of a constant thickness. The dielectric thickness expands with reverse bias. So as a result, you end up getting a voltage-dependent capacitance, all right? And this depletion capacitance is the stored depletion charges in the depletion region. Now, it turns out in diodes or semiconductor devices in general, there's another form of stored charge, which is the stored mobile charges, the minority carrier stored charges, and that gives rise to what is known as diffusion capacitance. To understand this, now let's look at the diode in forward bias. So if I'm forward biasing the junction, the depletion region will collapse compared to in reverse bias. I inject holes, which are the majority carriers on the P side. And remember, we said that in an ideal diode, the holes travel across the depletion region without any generation recombination. But of course, in a practical diode, you could have some generation recombination in the depletion region. But anyway, this majority carrier holes go across the depletion region, and now they become minority carrier holes in the N side. I have more holes over here than in the rest of the diodes. Very, very far away, the hole concentration would be Ni squared divided by Nd, if Nd is the doping level on the N side. Now, if I have more holes over here than over here, that establishes a concentration gradient. And anytime you have a concentration gradient, we know we'll have a diffusion. Now, the diffusion profile we saw by looking at the continuity equation for a long diode. Long meaning, who remembers what a long diode means? What's long? Anybody? Is
Longer
one
than the diffusion length.
very good. Yeah. So the measure of longness is how much longer than the diffusion length it is. Okay. And the rule of thumb is if the length of this region is longer than maybe 3 to 5 times the diffusion length, you can kind of ignore the growing exponential term that you have in general, right? Remember, when you solve the continuity equation in steady state, we got a decaying exponential e to the power minus x over LP with a prefactor, plus a growing exponential e to the power plus x over LP with another prefactor. But for a long diode, you can ignore the growing exponential term because that would blow up to infinity. But in a short diode, you kept both terms, and that's why you ended up with these hyperbolic functions that we solved at the end of the last class, right? So anyway, let's look at a long diode to begin with. So I only have the decaying exponential term. If I have a decaying exponential concentration profile, how do I get the diffusion current? Well, diffusion current is minus Q dP, the diffusion coefficient, times dP dx, or d delta p dx. The nice thing with an exponential dependency is if I take the derivative is also an exponential function. So the current, diffusion current, would also have the same shape as shown over here. Now, this is kind of strange because it seems to indicate that my diffusion current is disappearing, which it is, but the total current across junction must be constant, right? According to KCL. Now, who remembers what makes the total current constant? This is a refresher of the IV characteristic derivation. What do I have very, very far away from the junction? What is the current due to? Do you remember?
Majority carrier drift.
Excellent. Very good. In general, at any cross section, you have four components of the current, right? You'd have majority carrier drift, in this case, electron drift. Here it's hole drift. But let's look at this cross section. So at any cross section, it would be majority carrier electron drift plus minority carrier hole drift. But between the two, which component of the drift current can I ignore? Drift currents are proportional to electric field times the carrier concentration. Therefore, I can ignore the whole drift current, right? On top of that, I have to add the electron diffusion current plus the whole diffusion current, right? Well, very, very far away, there's no concentration gradient at all. Therefore, the diffusion currents for both electrons and holes would disappear, right? So very, very far away, it has to be only electron drift current. Similarly, over here, it has to be whole drift current. These carriers are injected, and the holes now become minority carrier holes. It becomes minority carrier diffusion current, right? And all these components self-adjust itself so that the total current at any cross section has to be constant. So that was a refresher of the IV characteristics, okay? Now with that refresher, now let's look at the capacitance, okay? So once again, capacitance is stored charge, right? Now the stored charge that I'm looking at over here is not the depletion charges that I discussed a few minutes ago, but the injected mobile minority carrier charges, all right? How would I get the total stored charge? Well, this stored charge depends exponentially on distance as e to the power minus x over LP. How would I get the total stored charge? You have to figure out the area under this dotted line, right? What do I get if I integrate an exponential? Nice thing is you still get an exponential, except that now LP appears in the numerator, right? If I take the derivative, LP appears in the denominator in the case of the currents, but in the stored charge, if I integrate the distribution, I get LP in the numerator, right? Then I take the limits of x equal to 0 to infinity to get the total stored charge. How would I get the capacitance? Well, these are once again voltage dependent capacitance. So whatever the stored charge is divided by the change of that. So if I increase the forward bias from V to V plus delta V, the new stored charge might be given by this solid line. So I get the difference of the stored charge, dq, divided by dV, and that'll give you the diffusion capacitance, all right? Now one finds that the stored charge is exponentially dependent on voltage. Do you remember that? Because this delta P was given by Ni square over Nd e to the power QV over KT. That was the total value. But then you have to subtract the background, Pn naught. So end up getting a delta P was Ni square over Nd e to the power QV over KT minus 1. Okay. And over here, what I'm showing is the delta. And therefore, I subtract the constant background minority carrier distribution. And therefore, the delta goes down all the way up to 0. Now, in forward bias, if you have e to the power QV over KT minus 1, since I'm looking at a forward bias positive V, I can kind of ignore the minus 1. That's what I've done over here. And the bottom line is, if I take the derivative of that with respect to voltage now, I still get an exponential dependence on voltage, but this Q over KT appears in the prefactor as shown over here, okay? So I end up getting a diffusion capacitance, which changes, increases exponentially with forward bias, all right? Now, if I also teach this class, 10 years ago, that's where I would stop, okay? But interestingly enough, approximately about 10 years ago, people took a second look at this expression for the diffusion capacitance, which was in textbooks for the last 50 years. Okay, people thought that this is a very straightforward device, and this is the expression for the diffusion capacitance, right? Because what I've just told you sounds perfectly reasonable, right? Because I figure out the total stored charge at some voltage V, then I figure out the change of the stored charge with dV, and I get the dq dV, and I get this expression, which is this exponentially increasing diffusion capacitance with forward bias, right? It all sounds very, very reasonable. And like I said, this was what was in the textbooks for about 50 years, okay, ever since PN junctions were used or discovered or whatever. But then about 10 years ago, a couple of folks took a second look at it, and they realized a flaw in that argument. Okay, and the flaw was the following: they said that when I look at dq over dV, I need to be consistent in terms of my definition of where I'm looking at the change of charge, at what electrode I'm looking at the change of stored charge, and the electrodes that I'm looking at in terms of the applied voltage, right? I mean, I can't, if I think of a capacitor with multiple terminals, it's not valid to think of changing the voltage across two electrodes and then measuring the charge across two other electrodes, right? I mean, that's kind of an inconsistent definition, right? And it turns out, if I have a long diode, as shown over here, there's an inconsistency in the argument, right? Because here I'm applying the voltage across these two external electrodes, but yet I'm measuring the change of the charge internal to the thing, and none of that change of charge actually is seen at the external electrodes, because all these minority carriers recombine entirely within the diode, right? Therefore, the dq for a long diode is actually zero. The extracted change of minority carriers as a function of the applied voltage for a long diode is zero. And as a result, for a long diode, the diffusion capacitance actually vanishes, as shown by this dotted line. However, for a short diode, where the carrier concentration changes linearly with distance, I can extract the minority carriers, and this exponential dependence of capacitance, diffusion capacitance, and voltage is valid. Okay? So you have to think in terms of what's called the reclaimable stored charge, meaning how much of the stored minority carrier charges can be reclaimed as electrodes, is what gives rise to the diffusion capacitance. It's a little bit of a tricky argument. Okay? All right. Now, once I have this idea of capacitance being the ability of a circuit element to store charge, that then leads naturally to the idea of time-dependent behavior of devices. All right. Now, because we've lost some time and because of the semester getting messed up, although I'm going to go through the analysis of the time-dependent behavior of diodes, I will not test you on that in the exams. All right. However, it's such an important topic. I hope that you pay attention and don't go to sleep and look at Netflix videos on the side. But you will not be tested on this in the exams. Okay. So why do I end up getting time-dependent behavior if I have a capacitance in the structure? Okay, the reason is simple. If you remember what you studied in 411. In 411, remember we studied that across a capacitance C, if you change the voltage, you get a displacement current, C dV dt. So that tells you then that across a capacitor, you cannot change the voltage instantaneously, right? Because if the voltage across a capacitor were to change instantaneously, dV dt would be infinite. That would imply an infinite displacement current, and you can't have any infinite currents, right? So that tells you, therefore, that the voltage across a capacitor cannot change instantly, right? Because otherwise C dV dt would blow up. Similarly, the current across an inductor cannot change instantly, right? Because remember, the voltage across an inductor is L di dt, right? So voltage across an inductor can change instantly. Current across an inductor can change instantly, and voltage across a capacitor cannot change instantly, right? And that kind of leads to very interesting time-dependent behavior that I'm analyzing over here for abrupt one-sided, so it's a P plus N long diode, okay? Because it's a one-sided junction, I kind of ignore the depletion region on this side. The depletion region is mostly on this side. And I ignore the majority, I ignore the current contribution on the P side. The most of the current can be thought of as due to the injected minority carrier holes on the N side, and that is diffusing in this long diode, and therefore the concentration is dying down exponentially with distance, and therefore the current is also dying down exponentially with distance. And let's look at this current just for a second to refresh your memory about what I discussed a few lectures back. So what I'm claiming is that in this particular case, the total current is approximately equal to the diffusion current of minority carrier holes at the edge of this depletion region over here, okay? And that's this current over here. I can ignore the electron current on this side. Why can I ignore the electron current on the P side? I don't ignore the electron current because of the lower N-type doping. I ignore the electron current because of the much higher P-type doping, right? And that's that funny statement that I made earlier, okay? Because I said that if I wanted to double the whole current, I should not double the P-type doping. I should have the N-type doping. Why? I should have the N-type doping because P on the N side is given by Ni square over Nd. If I was to have Nd, P on the N side would double, and therefore the whole current would go up. And therefore the reason I can ignore the electron current concentration on the P side is the minority carrier electron concentration Ni square over Na is almost nothing, right? So the nice thing is in this particular case, the total current is approximately equal to the injected hole diffusion current. Now, as the whole diffusion current vanishes because the concentration profile of the injected holes dies down exponentially with distance, something has to kick in to keep the total current constant. What is that something? Well, very, very far away, that's majority carrier electron drift current. Okay. All right. So I'm making these assumptions simply to simplify the math. Okay. Now, hopefully, you can see, if it wasn't in a one-sided abrupt junction, you get a contribution on this side. The math becomes complicated. And there's no point in complicating the math. We just want to look at the essential physics, right? So for this simple case, a long diode, one-sided abrupt junction, what I do is I'm looking at the continuity equation applied on this side. But now I'm looking at the continuity equation in non-steady state. Okay, now what is the continuity equation? Well, that was a bookkeeping equation, right? We said that if we consider a small region between x and x plus dx, and you have current flowing in at jpx and current flowing out at jpx plus dx, if there's more current flowing in than flowing out, the concentration in that region, del P del T, would increase. But if there's more current flowing out than flowing in, the concentration in that microscopic volume would decrease, right? So then we are able to write down del P del T as the divergence of the current. And then you'd also have a generation recombination term, right? And what I've done is I've taken that continuity equation and I flipped terms around, and I've brought the del P del T term that you normally saw on the left-hand side over to the right side. And the divergence of the current that you normally see on the right side, I brought it over to the left side. So that's my continuity equation, okay? As I was telling some folks, and I forgot to bring my iPad to work today. That's why I unfortunately can't write on it. My apologies. Therefore, I'm lecturing from my desktop. But hopefully with the cursor, you can follow me along, okay? And anytime you have questions, just unmute yourself and ask questions, okay? So this is the continuity equation. I've flipped over some of the terms. This term normally we saw on the left-hand side, I brought it to the right. And this term I normally saw on the right-hand side, I brought it over to the left, all right? Next, what I do is I integrate both sides with respect to x between 0 being defined as this depletion edge, to some location x, all right? And then ultimately I take the limit of x going to infinity as shown over here. If we do that, on the left-hand side, if I integrate the del j del x, if I integrate that, I'll get the current itself at x equal to 0. which is my total current. Well, this is current density, total current will be that times the cross-sectional area of the device, minus integral at x, so that's my JP at x, and ultimately I'll take the limit x going to infinity. The JP at infinity would be 0 because my diffusion current of magnetic carriers goes to 0. On the right-hand side, similarly, I initially integrate from 0 to x with respect to x, and then ultimately I'll take the limit x going to infinity. All right. Now, what do I get if I integrate the excess stored charge integrated from 0 to infinity? I'll get the total stored charge, right? But now it's going to be a time-dependent charge. So that's my total stored time-dependent charge divided by the lifetime. And this term, I'll flip the order of integration with respect to x and the differentiation with respect to time. So I'll first do the integral with respect to x. So that'll give me my stored charge. And I move the derivative outside of the integral. So I end up getting d dt of the total stored charge. Okay. Now notice, this is nothing but a generalization of the steady state expression for the current that you derived a few lectures back using the so-called charge control model. If it's steady state, what happens to the second term, dq dt? Of course, that has to disappear, right? And then the steady state DC current, I, would be the total stored charge, which is the total area under this distribution. If this was the injected magnetic area charge distribution, divided by the lifetime. Recall, that is my charge control model for the current, right? We said that if I have a steady state distribution of carriers, if I integrate that, I get the total stored charge Q. And if they're recombining at a rate tau P, I have to replenish carriers at the same rate. Therefore, I get a steady state DC current, which is the steady state total stored charge divided by the rate at which they're recombining. But now I'm looking at the non-steady state case, and I have the second term over here, okay? So what you find is, if I inject more current than I need to sustain my steady state distribution, the total stored charge will increase with time. On the other hand, if I supply a current which is less than needed to supply this steady state distribution, the charge distribution will decay with time, as shown in this cartoon figure over here, okay? So you can basically have to solve this differential equation. You have to solve this differential equation for different initial and boundary conditions to get the time-dependent behavior, okay? And one such example is shown over here. So this is an application of this fundamental differential equation for time-dependent behavior of a diode. So the special problem that I'm looking at is I apply a steady state current, I, from minus infinity time minus infinity up to time 0. So up to this point, it's like a DC current. So I can ignore the second term over here, all right? And I get a steady state charge equal to I times tau P, right? See, if that is my steady state charge, that divided by tau P is my steady state current I, right? Now at time t equal to 0, I shut off the current, okay? I had hooked up the diode in a circuit with the battery, with the switch, and I open circuit the switch, right? Therefore, the current abruptly goes to 0. Now, you normally think that if my current abruptly goes to 0, the total charge would also abruptly go to 0. But that does not happen because it takes a while for these excess stored charges to recombine at a rate 1 over tau P. So instead, what happens is, since the current is given by dP dx, as soon as the current is forced to go to 0 by open circuiting the circuit, this gradient at this junction abruptly changes to a 0 slope. Because if the gradient changes to a 0 slope, dP dx would go to abruptly 0, right? And therefore the current drops abruptly to 0. But the total stored charge doesn't go to 0 abruptly because it has to decay at a rate 1 over tau P, and there'll be a time dependence of the stored charge e to the power minus t over tau P, okay? And that time decay time is known as your minority carrier storage time. So it takes a time certain time, which is called the minority carrier storage lifetime, for all the stored charges to be swept away. Okay, and that's important because during the time that the stored charges are still there, the diode has a low impedance state. Okay, it's only after all the stored charges disappear that the diode really goes to reverse bias and the diode goes to a high impedance state. Okay. Any questions? All right, so you can basically solve this differential equation for different problems to get time-dependent behavior. And this shows some cartoon solutions of that solution. So now I have a diode where I'm changing the applied voltage from forward bias to reverse bias in a periodic fashion. So I'm going from forward where the gradient is positive. And if I abruptly change to reverse bias, the current cannot go abruptly to zero. The current changes to a negative voltage, and that's shown by this negative gradient of the distribution. And it's only after the storage delay time, when all the stored charges are swept away, that I really develop the reverse bias across the junction and the current goes to zero, right? So if I sweep this voltage with a time period less than the storage delay time, the current would never go to zero. You would switch from a positive current to a negative current. On the other hand, if the time period t is more than the storage delay time, it would go from forward bias to reverse bias. So it's kind of interesting behavior. All right. Now, normally I'd, like I said, go through the this example solution. Since I'm not going to test you on it, I'm going to skip this. But basically, what you see is this is a worked out example. I can't remember if I've given you a homework problem like so. I might have. So, in that case, go ahead and solve the problem, but you don't have to study for this in the exams. All right. So in this particular example, I'm switching the current from some forward current IF1, and at time t equal to 0, I switched abruptly to another forward current IF2, and I want to solve for the charge stored in the diode. Okay, how do I solve that? Well, that's my master equation. And I have an initial condition at time t equal to 0, where the stored charge would be IF1 times tau p. That can be considered to be a DC case because this current IF1 flows for a long time, from time minus infinity all the way up to time 0. So, in this time period, it's basically like a DC current. But then at time t equal to 0, I switch abruptly to another current, IF2. So that would be given by this differential equation over here. Now, to solve this differential equation, you can use whatever your favorite technique is. But one very convenient way that hopefully you saw in your math class is the technique of Laplace transforms. Okay. If you haven't seen this or don't remember it, like I said, don't worry about it because you'll not be tested on this. But basically, in Laplace transforms, you convert a differential equation into an algebraic equation in terms of S. Okay. So the Laplace transform of this is that divided by tau p. The Laplace transform of a derivative is S times the Laplace transform of q minus the initial condition, and in this initial condition is IF1 times tau p. Now that becomes an algebraic equation in terms of S, okay? That you can solve very easily, and then you can take the inverse Laplace transform. So that's a very convenient way of solving the time-dependent differential equation over here. Now the solution makes perfect sense. Let's look at the asymptotic behavior. So one finds that if I look at time t equal to 0, I get e to the power 0, which is 1. For the first term vanishes. E to the power 0 is 1. So I get the stored charge is equal to IF1 times tau p, right? Exactly as I said over here. On the other hand, for time going to infinity, this term disappears, and the stored charge asymptotes to a new DC value, IF2 times tau p, right? But in between, you have a very complicated dependency in terms of this exponential time dependencies. Okay. Any questions? So that's all that I have about capacitance, which then also leads naturally to this idea of time-dependent behavior. All right. Now we'll revisit this when you start looking at transistors briefly. And we also point out that in a modern IC, when you have interconnects, they also have some inductances, and in a modern IC, inductive effects can also be important. I'll mention that in passing once we look at chapter 6 and integrated circuits. Any questions on capacitance or time-dependent behavior? All right, let's move over to our next topic then, which is hetero junctions. Now, so far, we've been looking at homojunction devices. And basically what it means is the material is assumed to be the same everywhere in terms of band gap and other properties. However, the doping is allowed to vary. So in this case, for example, it might be a silicon diode with the same silicon band gap on the P side, on the N side, but I'm allowed to vary the doping from P to N type doping. Okay? So variations of doping don't matter when I talk about homojunctions. Homo versus heterojunction refers to the semiconductor material itself or other kinds of materials. Changes of doping don't count in terms of homo versus hetero. All right. Now, the first kind of heterostructure that we'll be looking at is a metal semiconductor heterostructure. Okay. And this turns out to be very, very important because anytime you make a semiconductor device, such as a diode or a transistor, we know, of course, that the end of it, we have to connect it to the external world, and that's connected through metal wires, right? So you'd have a metal connecting your semiconductor device, such as a diode or a transistor. You'd have to have another metal wire on the other side, connected to a battery, and that's how you make a device, right? And in fact, that's what's shown over here, right? So you have a diode that has to be connected to a metal wire, to a voltage source, another metal wire, to this region. So that's a metal semiconductor junction. That's a metal semiconductor junction. And that would be an example of a heterojunction, a special kind of heterojunction, a metal semiconductor junction. Okay. Now, what we'll see is such metal semiconductor junctions can sometimes behave like a diode, which are known as Schottky diodes, or sometimes as an ohmic contact resistance. So that's going to be the topic of the next few slides. All right. To discuss such heterostructures, in this case, metal semiconductor heterostructures, or later on in a few slides, we'll talk about two different semiconductors. So that's an example of a heterojunction. So you could have, for example, gallium arsenide region connected to an aluminum gallium arsenide region over here. We saw examples of that in chapter 2 when you looked at gallium arsenide quantum wells sandwiched between two aluminum gallium arsenide high band gap semiconductors. So those are examples of heterojunctions. So for such structures, we have to introduce some terminology that's shown over here. Okay. Now the terminology is in terms of your vacuum level, which is this line at the top. What is a vacuum level? Well, the vacuum level is a reference potential energy with respect to which we measure all the other relevant potential energies in the system. You might recall that when I look at a band diagram of a semiconductor, what we are plotting is the electron energy going up as a function of position in the semiconductor. Now, the electron energy, of course, has two components. We said that at the band edge, it's only electron potential energy. And as you move up, you add kinetic energy of the electron. Similarly, at the valence band edge, it's only whole potential energy. And as you go down, you increase the whole kinetic energy, right? Now, if you look at whole electron potential energy, we know, of course, also that potential energy is a relative quantity. So you have to ask yourself, potential energy measured with respect to what, right? And as I've told you, a very convenient reference potential energy is the so-called vacuum level, which is if I yanked electron out of the semiconductor and moved it very, very far away into space where it's not seeing any electric fields, I define that as my reference potential vacuum level, right? And that's shown by this horizontal blue line over here. With respect to that reference potential energy of the vacuum level, you can then define several important parameters. The first of that is known as electron affinity. The electron affinity chi in energy units is Q times chi, is this energy. And by definition, it's the difference in energy between the vacuum level and the conduction band age. So that's my first definition. The second definition is known as the work function phi. In terms of energy units, that's electron charge times phi. So phi or chi have voltage units, and Q times phi and Q times chi have energy units. So it's electron volts and joules. So phi is known, Q times phi is known as your work function, and that by definition is the energy difference between the vacuum level and the Fermi level. So two definitions, right? The electron affinity, which is the vacuum level to the conduction band age, and work function is the vacuum level to the Fermi level. All right. The other energy that's important, of course, is the band gap. So if I know what the band gap is, once I know the electron affinity, I can pinpoint what the conduction band age is, and that plus the band gap will pinpoint the valence band age. So the electron affinity, the band gap, and the work function enables you to pinpoint the conduction band age, the valence band age, and the position of the Fermi level with respect to this reference vacuum level, which is constant everywhere. On the metal side, metals we know don't have a band gap, so you only can define a work function of the metal. Here I have the work function of the semiconductor phi s. Here I have the work function of the metal phi m. There is no band gap, so you can't think in terms of a conduction band age, electron affinity, and so on and so forth. All right. So in this particular example, I've chosen a metal which happens to have a work function higher than the semiconductor work function. Of course, I could have chosen a metal the lower work function, in which case the EFM would be higher than the EFS. Now, when I join the metal and the semiconductor together, remember we said that we have electrons and holes which can spill over. And what describes which direction they'll spill over is the relative position of the Fermi level. All right. Who remembers which way the electrons flow? Do they flow from the electron-rich region to the electron-poor region? Or the other way around? Or is it something else that needs to be thought of, looked at? Anybody?
I mean, electrons could flow from high electron concentrated regions to low concentrated regions, but also have to take into account external electric fields. So I guess it would depend, really. Not really familiar with this subject, but
yes, you're exactly on the right track. So it's not just electron concentrations which determine diffusion, but also the electric fields, and therefore the total driving force is a sum total of the electrostatic potential, which defines electric fields, and the concentrations, which is determined by which determines your diffusion current, and the concentrations give rise to something called the chemical potential. And the sum total of the electrostatic and the chemical potential in physics is known as electrochemical potential, also known as a Fermi level. And therefore, the answer to my question is electrons will flow from the high Fermi level region, or the high electrochemical potential region, to the low Fermi level region. Okay. So your earlier answer that electrons will flow from the high concentration to the low concentration region assumes there's no variation of the electrostatic potential, no electric fields. Okay. So you have to generalize that in the presence of both electric fields and concentration gradients. And then the answer becomes it will flow from the high electrochemical potential or high Fermi level region to the low Fermi level region until in equilibrium, the Fermi level has to be constant everywhere, as we discussed when we looked at PN junctions in equilibrium. Okay. So in this particular example, although typically you'll have a lot more electrons per unit volume in a metal than in a semiconductor, yet electrons will flow from the semiconductor to the metal in this particular case. On the other hand, if I had chosen a metal with a lower work function, electrons would have spilled over from the metal to the semiconductor. But in this particular example, it'll spill over to the left. Now, if electrons, which are the majority carriers in the semiconductor, spill over, what happens? That'll create a depletion region, as shown by this lightly shaded region. And in the process, it will expose positively charged immobile donor ions. Now this should create a feeling of deja vu. It's kind of like a PN junction, right? Except that it's not a PN junction, it's a metal semiconductor junction. But the IV and the CV characteristics will look remarkably similar, and that's why these are also known as diodes. They're called Schottky diodes, after Walter Schottky, a German physicist, who analyzed this behavior, okay? So the rest of the analysis, surprisingly, is very similar to that for a PN junction, except that on the P side, I now have a metal, and of course in a metal you can't have any dopants, there's no depletion region, and you end up getting a very weird band diagram as shown over here. Now let's see if we can figure that out. Now how do I draw the band diagram? Well, as I told you in the context of the band diagram of a PN junction in equilibrium, the very first thing that you should do, you should close your eyes. It's very important that you close your eyes, otherwise it doesn't work. That's a joke. I don't want you to close your eyes in the final and not be able to answer your question. Anyway, you first draw a horizontal line with your eyes open or eyes closed, I don't care. You then draw the band diagrams far away from the junction, because I don't know what's happening right at the junction itself, but very, very far away is reasonable to assume that the carrier concentrations don't change before and after contact. So far away from the junction, you draw the conduction bandage as far above the Fermi level before contact and after contact. Same with the vacuum, with the valence band, it's of course farther away because it's an N-type semiconductor. The difference between the two is a band gap that can change. So the two lines for EC and EV have to vary in parallel. Now the tricky part is this region, right? I mean, how do you draw that? Now, in the final exam, I will ask you to draw band diagrams of either metal semiconductor junctions or hetero junctions. So I want you to be very comfortable drawing band diagrams of such heterostructures. So I'll repeat this several times because it's a very important topic and you have to be very comfortable with that, okay? All right, so how do I draw this part, okay? Well, I've seen already that the majority carriers are spilling over. I'm forming a depletion region. Therefore, I have less electrons than I normally have. As a result, the bands have to bend upwards, indicating that I have a depletion region with a depletion width of this much, okay? The tricky part is this side, okay? How do you draw this band offset? But to do that, you have to look at the band edges just before contact, and you extend them to see how the lines terminate, okay? So what you find is the height of the barrier over here is phi m minus chi, right? So the height of the Schottky barrier is phi m minus chi. You can kind of see that if you extend these lines, right? So that's my Schottky barrier height over here. There are no depletion regions that can form in a metal, right? Therefore, these electrons, they spill over, form a charged dipole right at this interface. But on the semiconductor side, the dopants that are exposed can form a depletion region, which forms a certain depletion width, as shown over here. All right. The resulting band diagram looks kind of like that of a PN junction. Of course, in a PN junction, you'd have a depletion region on the P side also. But other than that, it looks kind of similar to a PN junction. And therefore, the CV characteristics and the IB characteristics also will be very, very similar. I'm not going to go through the detailed derivation of the IV and the CV, but you have to have a qualitative understanding of that. So as in the case of a PN junction, here also in a Schottky diode, if we apply a forward bias V that appears mostly across the depletion region, because that's the most resistive part of the structure. The metal is highly conductive. The undepleted part of the semiconductor is also pretty conductive. The depletion region, on the other hand, is very, very resistive. For most of the voltage appears across the depletion region, and that will reduce the barrier if it's a forward bias, V. On the other hand, if it's a reverse bias, the bands get skewed in the other direction and the barrier goes up. In forward bias, what's going to happen is, well, let me go back to the previous slide for a second. So once I have this band diagram in equilibrium, once again, I'll have a dynamic equilibrium, meaning that the electrons at the N side can still spill over, but now they have to spill over this energy barrier. And as a result, it's only these high energy electrons high up in the band which have enough energy to go across. But that carrier flow of electrons have to be counterbalanced by high energy electrons on the metal side which go across, right? That's what establishes the dynamic equilibrium. Once I apply a forward voltage, I have more electrons at these lower energies, therefore they can spill over. But on the other side, the reverse current cannot change, because you can see that this barrier does not change with forward bias. And therefore, as a result, you'll get a current which exponentially increases with the applied forward bias. So that's this exponential increase of the electrons spilling over this way, but the opposing current is fixed because this barrier height is fixed, right? Now the prefactor, it turns out, will have a different form than the prefactor that you had in the case of a PN junction. I'm not going to go through the derivation of that. If you're interested, you have to look at a graduate level textbook, but let me point out what the terms are. So the prefactor is some constant A star. Here A is not the area of the device. A is known as your modified Richardson constant. Richardson was a British physicist to analyze this sort of a behavior. This is known as thermionic field emission. He won the Nobel Prize in Physics for that analysis. T is temperature in Kelvin raised to the power 2, e to the power minus phi b. Phi b is the so-called Schottky barrier height, okay, divided by Vt. Vt is your thermal voltage, KT over Q. E to the power V applied. That could be forward bias V or reverse bias VR, minus VR. If it's minus VR, of course, this term drops out and I get a constant current simply given by this prefactor. So the point is, the shape of the IV looks very similar to that of a PN junction diode, but the functional form is different in terms of the prefactor. You could similarly do an analysis of the CV behavior of a Schottky diode. Once again, you can define the capacitance as charge over voltage. You have to define that as change of the depletion charge over change of the applied voltage. And once again, it will be very similar to that of a parallel plate capacitor. Here it's shown as a function of unit area. If it's for the total capacitance, that will be epsilon semiconductor times the total area of the Schottky diode divided by the depletion width, which is a voltage dependent quantity. Okay. So that is a metal semiconductor device where I have a metal work function that I've chosen such that I form a depletion region. Okay, and that gives us to a diode type behavior, a so-called Schottky diode. The important takeaway over here is when you draw these heterostructures, you have to first consider the reference vacuum level. And with respect to that, the three energies that are important. First is electron affinity, which by definition is the difference between the vacuum level and the conduction band edge. The work function, which by definition is the vacuum level to the Fermi level. And then the band gap, which you have already seen. So with those three parameters, you can pinpoint the location of the conduction band edge. That plus the band gap pinpoints the position of the valence band edge, and the work function pinpoints the position of the Fermi level. Okay, and then on the metal side, I have the work function of the metal, and then when I join them, which way the carriers flow depends on the relative positions of the Fermi levels. Electrons will flow from the high to the low Fermi level region. Holes, on the other hand, will flow from the low to the high Fermi level region. Okay, so on Wednesday, we'll carry on this discussion. And just as a preview, here I'm once again looking at a metal semiconductor junction. Okay, but now I'm looking at a p-type semiconductor. Okay, now which way do the electrons flow? Well, electrons flow from the high to the low Fermi level region. In which case, in this particular case, the Fermi level happens to be higher in the metal. I've just chosen a metal with a lower work function than in the p-type semiconductor. Now, in terms of the semiconductor, it always makes sense to look at the flow of the majority carriers. Okay, since now I'm looking at a p-type semiconductor, it's the holes that I'm interested in. The holes, remember, will flow from the low Fermi level region to the high Fermi level region, right? If the holes spill over, I once again get a depletion region. The valence band moves farther away. Therefore, I form a depletion region, a barrier for the holes. So once I get a Schottky barrier, but now between the metal and a p-type semiconductor. Okay. On the other hand, going back to the n-type, if I chose a lower work function metal, what's going to happen? Electrons will spill over this way. On the N semiconductor, I have majority carrier electrons. Now the electrons are not spilling over to the left. I have electrons spilling over from the metal to the semiconductor. If I don't form a depletion region, I form a charged dipole of mobile electrons and plus charges on this side. There is no depletion region forming, no barrier. Now this guy tries to very easy current flow between the metal and the semiconductor, and such devices are known as ohmic contacts, okay? Because I have a linear IV, I don't have an exponential IV as you have in the case of a Schottky diode. These are called ohmic contacts, and you can have that for N-type or P-type, and that's where we'll start off on Wednesday. Okay? Any questions? All right, see you on Wednesday.